Alright, so this is a continuation of our discussion on coordination compounds. This time we're going to talk about nomenclature of coordination compounds. There's a lot of rules here. Some of it's borrowed from naming ionic compounds, some of it's borrowed from naming covalent compounds. Some of it may seem familiar, but I don't think it will be as bad as it seems at first after we go through a couple of examples. So we've got quite a few rules to go through here before we can get to some examples. So first of all, you name cations first and anions second, right? That's just like we do with ionic compounds. So for example, NaCl, you call it sodium chloride. You don't call it chloride sodium. You don't put the anion first. You put the cation first in the name and in the formula. So cations are first, followed by anions. Now remember, the complex ion might be the positive part of the molecule, or it might be the negative part of the molecule. So when we name complex ions, the names of the complex ions are given without spaces. The only space occurs between the name of the cation and the name of the anion. So the complex ion, the name of the complex ion itself can get pretty big, but however big it gets, that's all one word. The only space is between the name of the cation and the name of the anion. So how do we name complex ions? Names of the complex ions begin with the ligands. You name the ligands first in alphabetical order, and you name anionic ligands first and neutral ligands second. Then the name of the metal, and then the oxidation state of the metal, right? So it's the name of the ligands, the name of the metal, and the oxidation state of the metal. So the names of anions are changed when they function as ligands. Ide endings become changed to O, ate endings are changed to ato, and ite endings are changed to ido. Now if you sit down and think about this, you're used to doing this. Similar, you're doing something similar to this. For example, in the sodium chloride, think about the sodium chloride example that I used earlier. We don't call it sodium chlorine. We call it sodium chloride. So you're changing the name. You're changing the name of the negative part. So you've kind of sort of seen this before. All right, so chloride can be a ligand. When we name it, when it functions as a ligand, when we name it as a ligand, it becomes chloro. Okay? Hydroxide becomes hydroxo. Carbonate becomes carbonato. Oxalate becomes oxalato. And acetate becomes acetato. So we're changing these so that they end in, most of these we're changing so they end in ato. All right. So remember these ambidentate ligands that we talked about in the previous video that have different modes of attachment. This has to be addressed in the nomenclature system because every compound has to have a unique name. So we give these two different names depending upon the mode of attachment. So for nitrite, which is NO2 minus, if it is incoordinated, we call it nitro. If it's O-coordinated, we call it nitrito. The nitro form is the most common. But remember we said it's ambidentate, it can coordinate through the O or through the N. Okay? Cyanide is another example. All right? If it's coordinated through the carbon, it's cyano. If it's coordinated through the nitrogen, it's isocyano. Thiocyanate, SCN minus, it's thiocyanato if it is S-coordinated, and I'm sorry, thiocyanado if it's S-coordinated, and isothiocyanado if it is N-coordinated. Okay. Now, neutral molecules are given the same name as the neutral. So let's put it this way. Neutral molecules, when they function as a ligand, they're given the same name as the molecule. But some ligands have special names, and these are the most common examples. So, for example, when water functions as a ligand, it's given the name aqua. When carbon monoxide functions as a ligand, it's given the name carbonyl. When ammonia functions as a ligand, it's given the name amine. And yes, the spelling is correct. It's supposed to have two M's in it. Amine. And NO is nitrosyl. Okay? Now, you've seen this before too. When more than one type of ligand is present, numerical prefixes are used to represent the number of the ligands present. So, like I said, these you've seen before. We're typically, for our class, we're typically probably not going to go higher than 6, but it does go higher than 6. But that's 1 for mono, 2 for di, 3 for tri, 4 is tetra, 5 is penta, 6 is hexa, and so on. Now here we have a little bit of a wrinkle. If the ligand already contains one of these prefixes. Now we've already used this as an example. Ethylene diamine. Now ethylene diamine already has di in the name of it. And if, let's say, we had a molecule with 2 ethylene diamines in it, and we tried to call it diethylene diamine, that would get confusing. So instead, if your ligand name already has one of these prefixes, then we're going to use this alternate set of prefixes. That's 2 will be bis, we have 3 is tris, 4 is tetrakis, 5 is pentakis, 6 is hexa, and of course hepta is 7. Typically, I don't think I've ever seen this go higher than 3. Maybe tetra, but not too much higher than that. You don't run into this very often, going higher than 2 or 3. Now, these alternate set of prefixes, the bis, tris, tetrakis, are often used when you have multiple negatively charged bidentate ligands like carbonate and oxalate. So you'd say bis carbonato, tris carbonato, or bis oxalato, tris oxalato. Now, and whenever these prefixes are used, the ligand name is usually enclosed in parentheses. So you would say, if you had 3 carbonates, you'd say bis, parentheses, oxalato. Now, here's another name. There's another rule, rather. If the coordination compound contains a complex ion with a negative charge, then the name of the metal is changed so that it ends in ate. So in other words, if we have a negatively charged complex ion, then we have to change the name of the metal. So again, if something negative, you change the name. So cobalt would become cobalt-8. Nickel would be nickelate. Chromium would become chromate. And manganese would become manganate. Now, in some cases, the Latin name of the element is used. So, for copper, instead of saying copperate, which probably doesn't sound right, we call it cuprate. For iron, instead of saying ironate, we say ferrate. For gold is aurate, and silver is argentate. Okay? So let's go through some examples here. All right. So what about this first one? All right. So we have a complex ion. This is an example that I used in the previous video. We have a complex ion. We have a cobalt with 6 waters on it, and we have 3 we have 3 chlorides present, right? So the first rule said you name the cation first and the anion second, right? Just like an ionic compound. So here the complex ion is the positive part. So we would name the complex ion first and the anion second. So we say our name is going to be something chloride. Something, space, and then chloride. The only space is between the name of the complex ion and the name of the counter ion, right? Between the positive ion and the negative ion. So our name is going to be something chloride. So the rest of the rules are devoted to how we name the complex ion, right? So we have hexa, we have 6, that's hexa. So when we name the complex ion, it's the ligands followed by the metal followed by the oxidation state of the metal, right? So we have 6 waters, that's a hexa. Now water is one of those that has a special name. When it functions as a ligand, we call it aquo. So it's hexaquo cobalt 3 chloride. Okay, hexaquo cobalt 3 chloride. One more time, our only space is right there. All this is one word. The name of the complex ion is one word. The only space is between the hexaquo cobalt 3 space chloride. Okay. So let's look at another one. How about this one? So now the complex ion, right, is the negative part of the molecule, right, because we have this potassium sitting out front here. So this is the positive part of the molecule. This is the negative part. We name the positive part first, the negative part second, right? So we know our name is going to be potassium something. The something is the name of the complex ion. So complex ion, what do? We name the ligands followed by the metal followed by the oxidation state of the metal, right? So we have 4 nitros and 2 amines. Okay, so which do we name first? That was another one of our rules that said anionics get named first. If you know your polyatomic ions, you know NO2, that's nitrite, that's a -1 ion. Whereas ammonia, NH3, carries no charge. So we're going to have to put the nitro first. So it's going to be tetranitro diamine, right? So our full name is going to be potassium tetranitro diamine cobaltate 3. Now, here's where another rule came into play. Why do we say cobalt up here and cobalt 8 here? Because the complex ion is the negative part of the molecule. When the complex ion is the negative part of the molecule, we change the name of the metal so that it ends in 8. Now you might want to ask too also, how did I know the oxidation state of the cobalt is 3? This is why you have to know the charges on the polyatomic ions, right? If we have 1 potassium sitting out front here, okay, we know potassium is always +1 because it's an alkali metal. That means the complex ion is negatively charged. We have 4 nitrites. Each one of these is -1. We have 4 of them, right? So this is going to be -4. So +3 -4 makes this a -1 complex ion, which is why we had to have 1 cation out front to balance that. Okay, here's another, and this one is pretty easy by comparison. All right, so we have a cobalt. We have a Like the first example, we have a positively charged complex ion with anions to balance the charge, right? So we're going to name the complex ion first, the anion second. So our name is going to be something space chloride, right? So the rest of the rule is how we name the complex ion. We have, let's see, we have 1 chloro and we have 5 ammonias. Which one do we name first? Let's see. A comes before C, right? So we name the amine first, correct? Wrong, right? Anionics. Chlorine is a negatively charged ligand. That has to be named first. So it's chloropentamine. So the whole name is chloropentamine cobalt 3. There's our space, chloride. Okay? What about this one? All right, let's see. What do we got here? Now, what's this thing? NH2, CH2, CH2, NH2. What's that? We've got 2 of them. That's basically the formula for ethylene diamine, right? So we have a copper complex ion. Copper is coordinated to 2 ethylene diamines. We have a sulfate out back for charge balance, right? So we know our name is going to be something sulfate. The something is the name of the complex ion. So how we name the complex ion? So we got ethylene diamine. So we're going to say we got 2 here, right? Or are you going to say di-ethylene diamine? So that doesn't sound right because the di from this, the dye that we'd be using here gets mixed up with the dye in the name of ethylene diamine. So we use bis, right? We're going to use bis. We're going to say our full name then is going to be bis, ethylene diamine, copper 2 sulfate. And notice I put the name of the ethylene diamine is in parentheses, okay? Whenever you use the alternate set of prefixes, you put the ligand name in parentheses. So it's bis, parentheses, ethylene diamine, copper 2 sulfate. All right, so what about this one? K3CO C2O4 3. So now we're going back to having a negatively charged complex ion, right? How do we know that? Because we've got cation sitting out front. This is the positive part. This is the negative part. So we know that our name is going to be potassium something. So what's the something? The ligands, followed by the metal, followed by the oxidation state of the metal. Now, if you know your polyatomic ions, C2O4, what is that? That is oxalate, which when functions as a ligand, we call it oxalato. So we got 3 of these. Now this is another case where we're going to want to use those alternate prefixes. So it's potassium, and there's our space, potassium tris, in parentheses, oxalato, cobaltate 3. Now notice again I changed the name of the metal. Cobalt becomes cobaltate because the complex ion is a negative part of the molecule. Alright, how about this one? CrCO6CO3. So now we're back to the complex ion being the positive part of the molecule. Alright, so our name is going to be something chloride, right? So something space chloride. So CO, what's that? That is carbon monoxide. Let's see, does that carry a charge? No, it does not. So how are we going to name this? Now, carbon monoxide is a neutral molecule, but it's one of those that has a special name. It goes by carbonyl. So our full name is going to be hexacarbonyl chromium 3 chloride. Okay, and how about this one? Here's a common molecule. It goes by the common name of potassium ferrocyanide. Let's give it its exact or full name, right? So now we're back to the complex ion being the negative part of the molecule. So our name is going to be potassium something. Okay, now CN, what is that? That's cyanide, correct? When it functions as a ligand, we call it cyano. Right, so we're going to say hexa potassium hexacyanoferrate 2. Now notice I had to change the name. This is one of those that has a special, one of those transition metals that has a special name when you change it, so it becomes ferrate. So potassium hexacyanoferrate 2. Now, one more time, how did I know the oxidation state of the iron was +2? You got to know your polyatomic ions, correct? Now, if you got 4 potassium sitting out here, that means the complex ion is a -4, right? So if we take away the potassium, this thing is -4. So what's the charge on a cyanide? This is why you have to know the charges on the polyatomic ions. Cyanide is a -1. And so therefore, this is a 6-. So therefore, +2 -6 makes the 4-, which is balanced by the charges. Think about it this way. +4, +2, -6 all adds up to 0. +4, +2, and -6 adds up to 0. Okay. How about this one? Alright, so Na2CO4. Alright, so our name is going to be sodium something, correct? Sodium something. So the something is the name of the complex ion. So we only have one type of ligand here. It's chloro. It's tetrachloro. So it's going to be sodium tetrachloro cobaltate 2. Okay? Sodium tetrachloro cobaltate 2. We have to change the name of the cobalt to cobalt-8 because it's the negative part of the ion. Couple more to go. Alright, now this one's a little bit more exotic. Alright, so we know our name is going to be something nitrate, correct? Something nitrate. NO3 is nitrate. So the rest of this is devoted to the name of the complex ion. So we've seen this before. We have amines and we have cyanos. Which do we name first? We have to name the cyanos first because they are the negative part of the molecule. So it's going to be dicyano tetraamine iron, and the oxidation state of the iron, nitrate. Alright, so dicyano tetraamine iron 3 nitrate. Now how do I know it's iron 3? Right, because we have 3 total -1 charges. Nitrate is a -1. Cyanide is a -1, so we have -1 here, -2 here. Ammonia doesn't carry a charge, so you know you're dealing with iron 3. And notice I said iron 3, not ferrate 3. We said ferrate up here because the iron is the complex ion was the negative part of the molecule, so iron becomes ferrate. Here the complex ion is the positive part of the molecule. Iron 3 -2 still makes this carry a +1 charge. That's why we had to have that's why we have an anion to balance the charge. Alright, last example. So our name is going to be potassium something. Okay, our name is going to be potassium something. The something is the name of the complex ion, right? So CN is cyanide. We got 6 of them, so it is going to be hexacyano. So our full name is going to be hexacyano-chromate 3. Now notice I didn't say chromium. I said chromate, right? Because, one more time, this is now the negative. The complex ion is the negative part of the molecule, so we have to change the name of the metal so that it ends in 8. So chromium becomes chromate. Up here we called it chromium because this was the positive part of the molecule. Here we're calling it chromate because it's the negative part of the molecule. Alright, so that's it for nomenclature of coordination compounds.